All right, so in today's lesson, we're going to be learning about momentum and impulse. In your textbook, we're looking at chapter 7 called linear momentum. All right, so we are sort of getting towards the end of our look at mechanics and the study of motion. And momentum is a special quantity of motion that was designated by Sir Isaac Newton. And I'd like to draw your attention back to dynamics and the concept of inertia. So remember that inertia is the property of an object with mass to resist any changes to its motion. So typically we looked at objects that were at rest, where V was 0. Now, we know that if you want to get an object to start to move, you have to apply an unbalanced force. And then the object will accelerate in the direction of that force, according to Newton's second law. But how about an object that's already moving? Okay, so an object that has velocity already, it also has mass and it's moving. And so what about the inertia of that object? Okay, that object, it wants to keep moving. It wants to resist changes to its motion. Remember that if you want an object to change its motion, or in other words, accelerate, either speeding up, slowing down, or change directions, you have to apply, again, an unbalanced force, an F net. So we are going to be looking then at moving objects. And so why do moving objects resist changes to motion? Think about you're holding, you've got a baseball glove, you're wearing a baseball glove, and your friend throws a baseball at you and you catch it. You know that the baseball makes a sound when it hits the glove, and I'm sure you could feel it, okay, in your hand underneath the glove, okay? And maybe your hand even moves back a little bit, okay? Why does that happen? All right, that baseball had mass. It was moving with the velocity v, and it hit the glove, and the glove applied an unbalanced force, bringing it to a stop, okay? And so this moving object, before it stopped moving, okay, had a special quantity of motion that Sir Isaac Newton calls momentum, okay? So momentum is a property of moving objects. Very important. So V is not 0. So that is what momentum is. It is a property of moving objects. So just consider this. We've got then an object moving. How about if we want to change the motion of the object? Let's think about speeding it up or slowing it down. Well, let's think about two factors that would affect the difficulty in bringing this about. So for number one, consider mass. Okay, imagine the stopping distance, okay, of a freight train versus a go-kart that both have the same velocity. So clearly, freight train, if we had, this is the line, okay, and this is the train, and this is the go-kart. If they're both moving with the same V, well, the train is going to take a lot longer distance to stop versus the go-kart. Now, this is assuming that the brake forces are equivalent, but why does the train take longer to stop? Because it has more mass. Think about you're sitting at a stoplight in your car, and next lane over there's a bus. Why do you appear to speed up faster than the bus? Okay, because the mass of your car is much less than the mass of the bus. So I hope that makes sense to you. The second is the velocity, and it should be pretty obvious. If we've got a pickup truck, so the mass is constant, and it's got two speeds. One, 0.5 kilometer per hour, and the speed two is 95 kilometers per hour. So we've got our line here, and this is V1, and that's V2, and we're looking at stopping distance. Well, clearly, okay, it's going to, whoops, I messed that one up. I got them backwards. So I will just erase that. We'll pretend that didn't happen. So V1, half a kilometer per hour, stopping distance maybe is that much, delta D. But V2, okay, the stopping distance is going to be much longer. So, and it's pretty intuitive. Obviously, you would know that if you're in a vehicle, the faster you go, the more distance it takes for you to come to a complete stop if the braking force is the same. So mass and velocity both are factors that impact motion and how we can change the motion. So Sir Isaac Newton, again, laid this down for us where he talked about this concept of the quantity of motion. So think velocity really is a quantity of motion. If you don't have velocity, you're not moving, your position is not changing. So we consider this quantity of motion to be called momentum. Okay, so momentum is a physical property of moving objects. It is a vector. And the symbol for momentum is lowercase p. So lowercase p is known as momentum. So how do we define momentum? Momentum is defined as the product of mass times velocity. Clearly, if you've got a zero velocity, you've got a zero momentum. Put this into an equation form. P, momentum, vector, equals m times v. P equals mv, and that is our definition of momentum. Now units. Okay, so if we're looking at our unit of momentum, well, mass is kilograms and velocity is meters per second. So if we multiply the two, we end up with kilogram times meters per second, and that would be the SI units for momentum. There is no special name, okay? Kilogram meter per second is the SI unit. So again, make sure that mass is in kilograms and velocity is in meters per second. So you might have to do conversions when we're calculating different examples. All right. So we've got some examples here, basic level, determining the momentum of an object. So we'll be given a mass, we have to be given a speed, and just make sure that mass is in kilograms and speed is in meters per second. So what is the momentum of a 145-gram baseball thrown at 148 kilometers per hour, which is the average speed of a fastball being thrown? So momentum, P equals mv. So we don't have mass in kilograms, so mass is 148 grams, and v is 148 kilometers per hour. So we need that in kilograms, mass, and we need that in meters per second for v. So we can do our conversions right in the equation. We know that grams to kilograms is divided by 1,000. So 145 divided by 1,000 kilograms times velocity, again, kilometers per hour to meters per second, is divided by 3.6. So we would take 148 kilometers per hour and divide by 3.6, and that would be our speed in meters per second. And you can calculate the momentum of the fastball. Okay, so 145 grams divided by 1,000 kilograms, 1,000 grams per kilogram, sorry, multiplied by 148 kilometers per hour, divided by 3.6, again in meters per second, and we get 5.96111. I believe we were taking this to three significant digits, so 5.96. Now we need a vector. Okay, so we'll just assume forward, so positive 5.96 kilograms, meters per second, and that is our momentum of the fastball. So I hope that makes sense. Basic calculation, that is solving for momentum. Now clearly, P equals mv, we could isolate any variable. M would be momentum divided by velocity, and velocity would be momentum divided by mass. So here in part B, we're solving just for that. We are solving for the velocity. So we have the momentum of a 155 kilogram football player. The momentum is 517 kilograms meters per second west. We know m, and we know momentum. What is the velocity in kilometers per hour of the player? Well, P equals mv, v equals momentum over mass. So 517 kilogram meters per second west, we'll put a negative in front for west. So negative 517 kg meters per second divided by 155 kilograms. And we can figure out the velocity pretty straightforwardly. So 517 divided by 155 gives us 3.3548. So 3.3548 meters per second. Sorry, 3.33548. So 3.33548 meters per second, but we want it in kilometers per hour. So we're going to times by 3.6 to get kilometers per hour. At 12.0077, and we want 3 sig figs, so 12.0. 12.0 kilometers per hour, and the direction would be west, and that would be the velocity of the football player. I hope these two examples give you sort of an introduction to solving for momentum or mass or velocity using P equals mv. Remember that P, momentum, is a vector, and you must have direction. Remember that mass must be in kilograms, and velocity must be in meters per second. Okay. We have a third scenario here where we're comparing the velocities of two moving objects. So a hummingbird has a mass of 9.52 grams. It's moving at 77 kilometers per hour south. How fast must a seagull of mass 2 kilograms move or fly in order for it to have the same momentum as the hummingbird? So if we're talking about the same momentum, hummingbird is h, seagull is s. The momentum of the hummingbird must equal the momentum of the seagull. We're saying they're going to be the same. How fast must the seagull fly for that to happen? So if we just expand, again, we know P equals mv, then we can expand both out. So the mass of the hummingbird times the velocity of the hummingbird must equal the mass of the seagull times the velocity of the seagull. And if we are, whoops, I wrote P, that should be V. So now we have the ability to solve for the velocity of the seagull. So MHVH equals MS VS, and that's our unknown. So now it's just a matter of substituting, solving for V. Again, mass in kilograms, V in meters per second. So the mass of the hummingbird is 9.52 grams. 9.52 over 1,000, because we're converting to kilograms, times the velocity of the hummingbird, 77 kilometers per hour south. So that would be 77, negative 77 for south, divided by 3.6. That's meters per second. And that's going to equal the mass of the seagull, which is 2 kilograms, times the velocity of the seagull. So it should be pretty straightforward what we do. We'll multiply both terms on the left and divide by 2 to get the velocity in meters per second. What we will do is to compare, just so we can compare to the kilometers per hour, we will convert to kilometers per hour after. Okay, so the velocity of the seagull then, we'll calculate that. So we will take 9.52 divided by 1,000, multiplied by 77 divided by 3.6, and then we will divide that by 2 to isolate VS, and VS is 0.10181. 0.10181 meters per second south. But we want to convert that to kilometers per hour just to get a sense of comparing the velocity of the seagull to that of the hummingbird. So we will take the 0.10181, and we'll multiply that by 3.6 to convert, and you get 0.36652, and I think we want 3 figs, so 0.366. 0.366 kilometers per hour south, which you can see then is much less than that of the hummingbird. So that would be the velocity of the seagull. Why does the seagull have to fly so much slower than the hummingbird? Well, the hummingbird has a very small mass, and the seagull has a large mass in comparison. All right, so if we just quickly here look at this, if we're saying momentum of the hummingbird equals the momentum of the seagull, the hummingbird has a very small mass, okay, with a very large speed. That would equal then, relatively speaking, a large mass of the seagull multiplied by a small mass, small velocity. So this is kind of a visual. If the two momenta are going to be equal to each other, well, if there's a large velocity, then the mass must be smaller, and if there's a large mass, then the velocity must be smaller. So that is why the velocity of the seagull is 0.3 kilometers per hour, whereas the velocity of the hummingbird is 77 kilometers per hour. I hope that makes sense. So we've just covered off the basics of momentum, which is again a quantity of motion defined as the product of mass times velocity. So what happens then when velocity is not constant? What happens when there is an acceleration? Well, we know from kinematics that acceleration changes velocity. We know from dynamics that an acceleration only occurs when there is a net force, when F net is not zero, and therefore there is an unbalanced force. And we know that the object then would either speed up, increase V, slow down, decrease V, or change direction. So what's going on here? Now, let's think about it as well, throwing back the concept of momentum. If velocity changes, okay, if there is a delta V, what does that do to momentum? So think about that example with the baseball and catching it in the glove. The baseball was moving just before you catch it in the glove, but then it stops. And you probably, again, feel that impact, that collision in your hand, okay? But clearly, the velocity is changing. It went from moving to not moving, and so, of course, the momentum of something that's not moving is zero. So therefore, this leads us to the idea that if velocity changes, there will be a change in momentum. Okay, there will be a change in momentum. So if delta V is defined as V2 minus V1, it only makes sense that delta P would equal P2 minus P1. Okay, so there will be a change in momentum. But if P equals mv, what is delta P equal? Well, mass doesn't change, okay, you keep it constant, so change in momentum must equal m times delta V, or m times v2 minus v1. So that would be a basic definition for change in momentum, besides the obvious final minus initial. Again, there should be vector symbols here above all of the vectors. Okay, so we'll move on. So momentum and Newton's second law. Newton's second law, of course, F net equals ma. So in order to change the momentum of an object, so think about a soccer ball is at rest and you want it to move forward, you obviously have to kick it. That's pretty much common sense. But from a momentum standpoint, you have to change the momentum of the soccer ball. It was 0, and if you want it to move forward or backwards, you have to give it, okay, that kind of momentum. And so the mass, velocity, or both must change. Now, if the mass remains unchanged, which is most often the case, and that's going to be our grade 12 bubble, where mass does not change. Clearly, if we're talking about like a rocket ship that has fuel inside the tanks, and as the fuel burns, obviously the gas escapes from the thrusters, and then the mass of the rocket does change. But we're not going to be looking at rocket science in this course. So we're going to be in the bubble of grade 12 where mass is unchanged. Therefore, velocity changes delta v, and we know that acceleration is causing that. And F net causes that unbalanced force. Two factors influence the amount by which an object's momentum changes. Number one, pretty obvious, the size of the force. The greater the force acting on the object, the greater its change in momentum. You want a ball to go further, you throw it harder. Pretty straightforward. The time interval in which the force acts. A force that is sustained for a long period of time produces a greater change in momentum. A force that is sustained for a long time produces a greater change in momentum than the same force applied only briefly. An object that's in motion, say a soccer ball kicked towards the goalkeeper that has an impulse applied to it, the goalkeeper kicks it out of the net area, will move with a different velocity. Thus, impulse will change the motion of a moving object. And so impulse is literally defined as a change, brings about a change in momentum. Back to this long period of time. In sports, we call that the follow through. So in any kind of sport where you launch a projectile or get something moving, right, coaches always talk about the follow through. The follow through, okay, in sports sustains that force for a long period of time and produces a greater change in momentum compared to a shorter period of time. So how is this all related to momentum? Well, before the force acts on an object, it has an initial momentum. After the impulse is applied, the momentum changes and it would have a final momentum. Okay. So we are going to then derive the impulse change in momentum theorem. Okay. So first of all, impulse is given symbol capital I, and it's equal to the product of force and time. So we would say that impulse equals F times delta T. If we were going to look at units, we'll box that. Impulse is equal to the product of force and time. Units, force is newtons, time is seconds. So Newton seconds would be the units of impulse. So the SI unit of impulse is a Newton second. Okay. Change in momentum, we've already decided or derived is mass times the change in velocity, or mass times v2 minus v1. All right. So we talked then about a force F causing a change in momentum over a period of time. F net must be then equal to the change in momentum divided by the change in time. And of course, we know that F net is equal to ma, according to Newton's second law. right? And if we can go back over here, the delta V is caused by acceleration. It's delta V over delta T, okay? So it does relate back to Newton's second law. So back over here, F net, the unbalanced force causes momentum to change, okay, per period of time. Well, if we know that impulse is equal to F delta T, okay, if we isolated delta P, we can multiply up delta T and we just replace F net with F. We know that it's F net, so we'll just call it F. Multiplied by delta T, and that equals change in momentum. And that comes back to the fact that F delta T is impulse, and that side is still change in momentum. So we have shown then that impulse equals change in momentum. The better definition here would be this. In fact, this is the impulse change in momentum theorem. It's usually how we state it. So impulse causes momentum to change. Think about it, impulse is a force applied over a period of time. If the soccer ball is at rest and its V is 0, and then over a period of say 0.2 seconds you kick it and its V is 10 meters per second, well clearly it's momentum change. Let's just call it a 1 kilogram ball. So momentum 1, 0 times 1 is 0. Momentum 2 is 10 times 1, 10 kilogram meters per second. So clearly there was a change in momentum. Went from 0 at rest to moving, okay, because you kicked it. You applied a force over a period of time. The amount of impulse you applied caused the momentum to change. If you kick the ball harder, maybe it's moving at 11 meters per second. And then it would be a final momentum of 11 kilograms meters per second. So I hope you understand then how this impulse change in momentum theorem works. So impulse, okay, is a product of force applied times time. That causes momentum to change. We've got some examples that we can look through here. So Tiger Woods, the golfer, hits a golf ball of mass 55 grams off a tee. We're going to assume the golf ball is at rest, so V1 is 0. It leaves the tee at 49 meters per second, so that would be V2. What impulse was applied to the ball by the club, and what is the change in momentum of the ball? So impulse is F delta T. But there's nothing here about force, but we also know that impulse equals change in momentum. Okay, so if we find the change in momentum, it is equal to the impulse. So change in momentum equals P2 minus P1. We don't know P1, we don't know P2, so we can use the other definition, M delta V. So the M mass is 55 grams per 1,000 kilograms times delta V. So V2 is 49 meters per second minus 0 meters per second, because we're assuming the golf ball on the tee is at rest. So when we solve here, 55 divided by 1,000 and multiply it by 49, you get 2.695. Kilogram meters per second. So the change in momentum of the golf ball, delta P, 2 sig figs, would be positive 2.7 kilogram meters per second. And it asks for the impulse. Well, impulse is equal to the change in momentum, so the impulse must equal positive 2.7 Newton seconds. So notice that impulse and delta P are the same. So our second example, we have a circus duck is launched from a cannon and has an impulse of 2.5 times 10 to the 3 Newton seconds. The mass of the duck is 15 kilograms. Part A, what force does the cannon exert on the duck if it takes 0.2 seconds for the duck to leave the cannon? So we know impulse, and we're talking about force. So Fi impulse equals F delta T. We want to isolate F. So F must equal impulse divided by delta T. So the impulse is 2.5 times 10 to the 3 Newton seconds. We'll assume it's forward positive, divided by the time, 0.2 seconds. And we can get our answer for we can get our answer force applied to the circus duck. So we take 2.5 times 10 to the 3, divide that by 0.2, and you get 12,500 newtons. 12,500 newtons. And I believe the sig figs, for 2 sig figs, positive 12,000 newtons would be the force applied to the circus duck. Part B, how long is the barrel of the cannon? How long? That looks like a delta D, which means kinematics. The duck leaves the cannon at 120 kilometers per hour. We'll assume that V1, the duck is 0. All right, so we're going to need to find the acceleration of the duck. From that, we need to use our dynamics, so F net equals A. The F net we calculated in part B, 12,500 newtons equals 15 kilograms. So the duck multiplied by acceleration. So the acceleration of the duck would be 12,500 divided by 15, and you get 833.3 repeating. So 833.3 repeating meters per second squared. It's a positive. And now we want to find the length of the barrel. So the length of the barrel, L, equals delta T. We know V1, we know V2, we know A, we want delta D, that's kinematic equation 5. 2A delta D equals V2 squared minus V1 squared. We know that the duck starts at rest. So delta D, the length of the barrel, is V2 squared divided by the acceleration doubled. 800, nope, not 800. We have to convert. The duck is moving 120 kilometers per hour. We want that in meters per second. So divide by 3.6. 120 divided by 3.6, we square that. And then we divide it by 2 times 833.3 repeating. So 120 divided by 3.6. Square that, and we divided by 2 times 833.3 repeating, and you get 0.666669, so 0.6667, so 0.6667 meters, and we needed 2 sig figs, so the length of the barrel of the cannon equals delta D. The length equals 0.67 meters. And that is just how we can take some stuff from our momentum unit and bring it back to kinematics to solve a scenario like we just did. So I hope these examples make sense. And there are some practice questions, page 188, numbers 1, 2, and 3 in your textbook. Tomorrow, you'll be working on a practice workbook. There's 2 sets of questions. The answers are provided in brackets. So practice those tomorrow. And if you have any questions, don't hesitate to email me. And good luck with learning momentum and impulse.